something that's occurred to me a number of times as we've been talking here is you talk about fluid dynamics is how when we model weather, this is also the similar kind of like fluid process. And I particularly started thinking about this when you were talking about, kind of supercomputers running for weeks. And I was thinking about how it's my understanding that a lot of our world's supercomputers are tied up with this weather simulation problem. That it's like, in order to be accurately able to predict weather changes up to even just a few days, that the amount of complexity of the fluid flows is so great that you have some of the world's biggest supercomputers doing those computations.
Well, let me rephrase this a little bit. I think a lot of really large computer systems were designed just to do that. Okay,
Right.
so yes, it's not as if the weather modelers come in and say, "Let me steal your computing time." A
Right.
lot of these systems were designed particularly to solve these really complex problems. So you're absolutely right. Weather prediction is one of them. Of course, weather prediction it has enormous impacts on societies. I mean, if we can improve that, that's why we're constantly chasing improved weather prediction. It can make an enormous difference on people's livelihoods and people's comfort. Just imagine if we were better at predicting tornadoes, formation of tornadoes, even better than we are now, predicting hurricane pathways, and so on. Um, and it's not just air weather. I always talk also about ocean weather, because we can certainly at coastlines be impacted by ocean weather. Is there a storm
Mhm.
surge coming? Right? Is there a tsunami traveling through? Um, are there extra big waves? Is the swell enormous? Should we worry about impacts of wave erosion? So all those things, ocean weather and air atmospheric weather are both really important for us. Impacts on agriculture, impacts on safety, you name it, comfort. So yes, we use enormous computer resources for that. There used to be a time where I can't remember how long ago, where it was still more accurate to say in a weather prediction, oh, the weather tomorrow is going to be the same as today. You had a higher chance of being right than believing the actual weather prediction. But I think we're past this now. Weather prediction is notoriously difficult in some areas of the world, particularly around big mountain ranges, at the confluence of places where there's often this confluence of high pressure, low pressure systems. It's tough work, this prediction, but we are much better than we were when I first started in this field. The other area that, of course, requires a tremendous amount of compute power too is climate modeling. So this is weather in the long run, sort of averaged weather patterns, right? And so you can imagine that if weather forecasting requires a lot of compute power, climate forecasting requires even more. Now, the scale at which you do climate modeling and the scale at which you do weather modeling is a little different, right? In weather modeling, we want much more resolution. In climate modeling, we cannot afford that resolution just yet, because then we would really be extraordinarily expensive.
Mhm.
So now other areas in computational mathematics that take an enormous amount of compute power is, of course, social media related data science. It's searching on internet engines, it's recommender systems, it's things like large natural language processing, large language models. Take a lot of work. It's optimization and running of our electricity systems, our grid systems. It's optimizing and running stock predictions, stock market analysis. Um, you know about Bitcoin, which is a variant of that. I mean, there are many, many systems that require a lot of time. It's design of certain um, products. Think about the compute power that is needed to help optimize the design of new airplanes, of cars. There
and
are
uh,
many,
and
yeah,
yachts.
Up yachts, of
That
course.
that's a particular interest for you, isn't it?
It used to be, yeah. When I lived in New Zealand after my PhD, I went to the United States for graduate school, and then after my PhD, I moved to New Zealand, which, by the way, was a natural progression for me because I grew up in Zealand, the old New Zealand.
The old Zealand.
The old Zealand. And Abel Tasman, who named New Zealand, was from that same area back in Holland. So that's hence the name New Zealand. So I always told my parents there's a natural progression. I'm moving to New Zealand. But when I was in New Zealand, I ended up working on coastal ocean flow because New Zealand is, an island and has, I think, 14,000 kilometers of coastline. So coastal ocean flow, super interesting. Estuary flow, really important. Auckland, by far the largest city in New Zealand, is right in between two coastal ocean systems, a large estuary, and then the Pacific side, also, which creates lots of interesting shallow water, flows on the continental shelf, pretty shallow. And on the other end, it's an estuary, and then the Tasman Sea, which is also pretty wild. So worked on coastal ocean flows for a bit because that's where the interest was in New Zealand, and also on yachting because New Zealand is pretty darn amazing as a country in sailing. A lot of very, very good sailors come from there. And there is this race called the America's Cup that New Zealand has won several times, Australia too, United States also, I must admit. Uh, but I got really interested with some of my students in the flow past sails. So how would you design sails on a competitive yacht used in the America's Cup so that you could go faster? And that was fascinating. I did in my PhD a little work on airflows, particularly for wing design. I didn't do wing design myself, but I worked on codes that could be used by wing designers. And sails are a bit like wings, but much more interesting because at that time sails were pretty elastic, pretty flexible, and of course we're moving around a lot. Nowadays in the America's Cup, for those of you listening who have watched the races over time, the sails have really been replaced by vertical wings, and there's much more rigidity to them than before. So the aerodynamics involved with that, the computational mathematics involved with that is much closer to what I used to know. But I started working on sails for a while, and one of my former students, Steve Colley, is still a member of Team New Zealand. He also worked for a couple of other challenges, but he's been back at Team New Zealand for a long time, and he's one of the main designers there. And that's just
Oh.
it's terrific. The if I don't know if you saw this, but the sail design that I worked on for a while also led me to the craziest project I've ever worked on in my whole life. And that was designing a wing, but the wing of a pterodactyl, a pterosaur, which, funnily enough, looked a bit like a sail.
Huh.
So anyway, yeah, that was a very interesting sort of segue for me in my research.